Well, we should go ahead and get started. I'm excited. This week we have a joint talk with Lina Dogra and Maciej Galka, who are presenting some of their recent results studying wave turbulence in Bose gases. And it's a joint talk, but as they were just saying, if you have questions halfway through, feel free to raise your hand. Otherwise, we'll leave them till the end. All right, have at it.
Okay, so thank you very much for the nice introduction and everyone for attending and listening to our recent results about wave turbulence. So Maciej is going to present you the dynamic scaling during the buildup of a turbulent cascade. And I will start now with presenting you our measurements of the equation of state of such a cascade. So first of all, equations of state are one of the most central concepts to modern physics, and they are so useful for us because they provide us with a very concise description of a system relating state variables that describe the momentary state of the system, but for which we don't need any knowledge of the exact microscopic processes that are going on or of the history what happened to the system before. Since the concept was discovered with the ideal gas equation of state, it was extended to many other systems and also used successfully to describe phenomena close to equilibrium, like the response of a system to small perturbations or linear transport phenomena. Still, a huge variety of the processes that interest us in our daily life, in nature, even in life itself and our own body, are far from equilibrium. And for such far from equilibrium processes, things are more complicated, many times because they typically involve dynamics that involve many very different length scales, and because the systems are so scrambled up that the equilibrium state variables are completely meaningless. Even locally, we cannot use thermodynamic equilibrium or thermodynamic principles to describe the system. Nevertheless, the goal is to find an equally concise description in analogy to the equilibrium thermodynamics. And in some cases here and there, that has been possible with the hope to extend and generalize it for more and more. And one broader class of systems where it feels a bit more natural to do so are non-equilibrium steady states. For one very famous example of such a steady state, I would like to present you our experiment now for turbulent cascades, which support such steady states. So if you have here this famous illustration of the Richardson's cascade, if we inject energy into a system at a large length scale, in a turbulent cascade, this energy will propagate to excitations at smaller and smaller length scales and eventually be dissipated at a length scale set by the viscosity. Now, for turbulence in general, what I would say more explored and more well known is turbulence in incompressible fluids, where a lot can already be concluded just based on dimensional analysis. And there is the very cornerstone result of the Kolmogorov-Obukhov 5-third law. This law we can already interpret as a simple relation between the energy stored in the cascade with the energy flux, denoted as epsilon here, transported by it. On the other hand, what we are going to show you today, what we are working on is a compressible fluid with wave turbulence. And there things get a lot more tricky because we have more scales entering the problem. So from the dispersion of our waves, we have another energy scale. And also from the contact interaction between the particles, we have another energy scale entering the problem, and it's less clear what's going to happen. But we try and explore this experimentally, which I would like to show you more now. So first of all, let me very briefly introduce you to our system and our protocol. We have potassium 39 in an optical box trap, as you can see here, with the homogeneous density distribution and with tunable interactions through a broad Feshbach resonance. So just via tuning the surrounding magnetic field, we set our interaction strength. Now to excite a turbulent cascade, we start with a Bose-Einstein condensate, and we apply a magnetic gradient along the axis of the trap, which we modulate periodically in time. First, this would simply excite sound waves, but driving for stronger and longer, the energy is also transferred to higher and higher excitations, and we get this turbulent cascade state. We drop the state by going to zero interaction strength and taking time of flight pictures. So an example momentum profile we get from these time of flight pictures is plotted here. We see the characteristic power law spectrum that's so typical for turbulent cascades, and which carries a constant energy flux in the steady state. So it's maintained from driving the system as I just showed you. It's small wave factors of the scale of the inverse system size, and the energy propagating to higher wave factors up to the dissipation scale, which in our case with an interacting Bose gas isn't set by the viscosity, which we don't have, but instead is simply set by the trap depth, which sets the maximum momentum that can be held, and otherwise atoms with higher momenta are lost from the system. And actually that atom loss is also what we use to probe the energy flux most reliably for us. Okay, so historically, it's probably fair to say most attention has been given to this exponent of the power law spectrum here. In our case, we measure about 3.2 as the exponent that best describes our data, actually at all the parameters that are experimentally accessible to us. And comparing this to theory, it's close to the analytical result from weak wave turbulence that predicts 3. And it's also known that there are some finite size corrections to this value. So much about the power law, but the momentum spectrum also has this coefficient here, the cascade amplitude or the Kolmogorov number, which is a bit less well understood. And let us look at this a bit more now. Okay, to see what's going on for different possible parameters of the cascade, let's vary something. Let's start with varying the dissipation scale. If we look at the spectrum, one can see a bit more in the compensated spectrum, just multiplying away the scale to the gamma here, and then the amplitude appears as a plateau. And what we see is between the gray and the orange curve, that is with different trap depths, so with different dissipative cutoffs. And we see that really it's just this cutoff of the cascade that changes, whereas the value of the plateau doesn't really depend on the dissipation scale for otherwise same parameters. Similarly, for the flux rate, we plot here the number of atoms lost from the system, and if we multiply this by the trap depth, so by the energy of these atoms, again we get the same flux rate for both of these cases. Now, on the other hand, if we vary the injection, so we vary the force of the driving, one example for this is what's plotted as the green curves here. We see that things do change quite a bit. And looking at this more, we take curves of the flux rate and of the Kolmogorov number as a function of the drive strength. We see that both of them increase, but we also see how much they increase actually depends a lot on the frequency that we use for the drive. So here it's a bit less tidy. How can we make sense of this? If if as a next step, instead of looking at these quantities as a function of the driving parameters, we hide the drive parameters and plot the energy flux and the Kolmogorov number in response to that against each other instead, we see that actually all these curves collapse into the same curve, and this is what we were looking for. This is an equation of state for this turbulent cascade, describing this cascade in terms of quantities that are really properties of the inertial range, so the energy flux it transports, and the amplitude, the Kolmogorov number, as the state variables, and independent of the boundary conditions in momentum space, so at higher or at lower momenta. Okay, for the functional form of this equation of state, we are slightly more puzzled. Let's say when we look at the rate at the increases, one starting point would be to say we see two regimes that are approximately power laws and fit those, as you can see here. And this, of course, is a bit inspired by our theory comparisons. The most established one being the weak wave turbulence result. So that's an analytical result, which predicts also a relation between this energy flux and the Kolmogorov number. And it predicts a pure power law relation actually with an exponent of 1/3. So this is not far away from what we observe here at lower at lower occupation numbers. Now this result is a perturbative result for a small nonlinear term, so it is expected to break down when this term gets too high, for example, through too large occupation numbers. Just like we also see here that the agreement with this 1/3 slope would definitely break down to higher occupation numbers. And on the other hand, what's the theory we would expect to hold for high occupation numbers? Of course, then we would more think of the Gross-Bitoyevsky equation and the corresponding coherent evolution. So for a comparison, doing a small GPE simulation ourselves exactly for the same parameters to compare with our experiment, actually we found again just one single power law with the GPE, and this time with a higher exponent, which is closer to this to the slope we observe on the other hand here of high occupation numbers. So this is what we have, let's say, a partial agreement with each of the theories in the different regimes of different occupation numbers. And in general, not necessarily for this equation of state, but also say for the earlier stages of the occupation, this also has been tested numerically, so benchmarking the wave turbulence theory against GPE by numerically simulating both, and it's quite an ongoing interesting problem. Okay, let's take a step back. These results we got by always starting with a ground state BC and exciting the turbulent cascade from there. But what we have for equilibrium thermodynamics is that one of the most useful properties is that the history of the system doesn't matter. So what happens if we start with a different state instead? For example, we start with a turbulent state and then see if we can quench between turbulent states and what happens then. So you see here the atom loss, you see the energy flux for such a case. In the orange curve, we have quenched the drive strength at the time of this dashed line here. And we see that indeed shortly after, there's a kink in the slope and the system is able to follow the different injection rate and go to the same flux as in the ring curve, which describes what happens when initially driving with the stronger driving strength. Also microscopically in the momentum profile, here we have the two steady states. And after the quench, we see additional cascade population propagating to higher and higher momenta, and ultimately reaching exactly the same state as our strongly driven state that started from equilibrium. Now, let's close the loop and do it the other way around. We quench down the shaking strength, which we plot here in the screen curve. And we see again from the initially more strongly driven steady state, slowly the cascade population decreases and the extra atoms go out, last at higher momenta until the same steady state is reached as when we started from equilibrium. So looking at the atom number in this inertial range, we can see it even more clearly. Shortly after the quench, we really just switch between these two steady state values, or in terms of our equation of state. We know now that this equation of state is single valued, and that quenches basically result in jumping between values there. Lastly, I would like to tell you about what we measured when trying to generalize this equation of state for different microscopic parameters of the ground state we start from. So in the legend panel here, you can see we varied the atom number and the interaction strength, so the scattering length here, and again measured the relationship of energy flux and Kolmogorov number. And we see that now a larger parameter space is spanned, so the relation isn't always the same. And the first thing we notice is that if the product of N and A, so basically the chemical potential which is proportional to this product, is the same, then these measurements, and that's something we really just see experimentally, end up more or less on one line. So these are the lines here with different markers, but similar colors. So the equation of state for one value of mu seems to be the same, but we are wondering, of course, can we somehow collapse all of those, since their shape looks quite similar in the vertical Kolmogorov number direction? We can just empirically try to collapse the curves by scaling the x-axis and finding more appropriate units for the flux. So, sorry. So, what works is to simply rescale this flux with the power law of the chemical potential mu, as you see here. So now we get one universal curve, rescaling with the power of mu that's actually even quite close to 1. But still, there are many, many open questions about this universal equation of state, because it agrees actually neither with the scaling that's predicted by the wave turbulence theory, nor with the scaling that would be consistent with the GPE. So that's the last and most ongoing thing I would like to show you. And I'm already at the summary. I showed you the turbulent cascades that we explore with our homogeneous Bosse gas as an example of a far from equilibrium steady state. I showed you how experimentally we construct an equation of state that relates as the state variables the energy flux and the amplitude of these cascades. We have seen that this equation of state holds independent of the system history. And we have seen that we can collapse those measurements for different system parameters onto one universal line. Now in the outlook part, I think the most puzzling thing is how to find out more about the universal characteristics of this equation of state, and in general more about the possible thermodynamic description. To extend the weak wave turbulence theory, understand its validity better, and in particular also understand more about the interplay of compressible and incompressible flows in the system. And then we have seen how from the ground state that's characterized by one equation of state and one set of observables, we go to this completely different far from equilibrium state And it would be quite interesting to understand more of the transitions between the two, which is what Maciek is going to talk about now.
Excellent. And thank you very much for showing these really nice results. If anyone has a few quick questions now, you're more than welcome to ask while we still have these slides up. All right, it looks like we'll save the questions till the end. So, all right, let's go ahead and swap speakers then. Thank you.
Okay. Do you see my slides? Okay, thank you. So I'm Maciek from Zoran's group, and as Lena already mentioned, I'm going to talk about the birth of the two-dimensional wave turbulence. And my presentation is based on the preprint, which we recently put on arXiv, and you can see it here. So, okay, what is turbulence? So we have some injection, we have some dissipation, as we learned from Lena. And the question which we want to answer now is how actually the energy gets cascaded to the dissipation scale such that the steady state turbulence is established. So first, we are taking a step back and we focus on the two-dimensionality of the system. So the two-dimensional systems are famous for inverse cascades, which in hydrodynamic fluids mean that the vortices with the same polarity pair up, as it is shown here in cold atom settings, but it also appears in classical fluids when giant vortices are forming. But our Bose gas is incompressible as well, so it allows also the direct wave cascade in two-dimensional system, and that's what we are going to focus on today. Additionally, we are going to take advantage of the dimensionality of the system, because as the system is two-dimensional, when we experimentally take the image, we do not need to integrate over any dimensions, so we get a full readout of all observables. So what do we actually expect in the formation of turbulence? If we imagine that this disk is our K-space, then we have some injection at large length scale, which corresponds to small k vector. And then the waves interact with each other, and we expect two additional concepts to appear. Essentially, that we expect that despite the anisotropic injection, usually we expect the isotropic cascade front for the system where there's no momentum flux, as in our case, where the gas is just confined. And the second concept is that in the pre-steady state, as the cascade is formed, then its front will propagate algebraically in time. And in general, the momentum distribution will follow the dynamical self-similar scaling. And these are the results of three-dimensional simulations. And you can see that the cascade is formed, so which is given by the power law. So in the steady state, we have the power law momentum distribution. And initially, a little bit of power law is there and the cascade front, and it propagates in a self-similar fashion. This self-similarity also links the pre-steady state turbulence to the proposed general classification of far from equilibrium systems, which is now formalized within the framework of non-thermal fixed points, where the idea is the following, that having this exponents alpha and beta, we want to classify the systems to the universality classes similar to the equilibrium systems. In case of turbulent cascades, we are not completely lost in terms of what kind of exponents alpha and beta we expect, as there are some constraints coming from the fact that in the steady state, we want the power law momentum distribution. And this means that alpha, beta, and gamma are related. And additionally, as we shake our gas or just inject energy, we inject it usually, or we assume here that we inject at a constant rate, and it puts the second constraint on the exponent, which gives the form that the beta exponent and the gamma exponent is related with the dimensionality of the system. So with this background in mind, we can now look at our experimental setup. What we have is a two-dimensional uniform box trap, which is formed from optical potentials, both sculpted using digital micromirror devices. So to form a two-dimensional box, we need two components. We need repulsive walls, which is red here, and we need tight vertical lattice, which forces all the dynamics to be two-dimensional, which is provided by the Fourier imaging of two beams. So we start with loading the atoms to the trap, and we start with the essentially pure superfluid. And the excitations in such a system follow the Bogoliubov dispersion relation. So initially, we inject energy to the phonon modes, which are discrete because of the finite size of the system. And then as the energy will flow towards higher K around our inverse healing length, the excitations change its nature from phonon-like to free particles, where eventually at the dissipation scale, which as Lena mentioned, is set by our trap depth, they are dissipated as free particles. So already at this stage, we can put some requirements for our experimental system. First one is that we want our dynamics to be two-dimensional. So all the scales in the system involved needs to be smaller than the vertical harmonic oscillator spacing. And also it's also important for our dissipation scale to be then smaller than our vertical harmonic oscillator spacing. Secondly, we want to study actually this free particle regime, mainly because that's what we are able to measure, because in time of flight, we actually measure the atomic distribution. So we want this range to be as large as possible, which means that we want to push this k psi to as close to kf as possible, and thus UD needs to be much larger than the chemical potential. And solution to that is just to go to weakly interacting both gases, and we use G tilde smaller than 0.1. To cover such a broad range of case, we use 3 different experimental techniques. At large case, we use time of flight, which gives good signal to noise ratio, but it's fundamentally limited due to finite size effects. And at very low K, we use principal component analysis to study density modulations in situ, and to link these two regimes, we use Bragg spectroscopy, which doesn't have the finite size problems, but also doesn't have the resolution for discrete modes as PCA has. Okay, so if we complete our cascade picture, now we can put the scales that we have the injection on the system size length scale, then the phonons change to free particles, and then eventually, after the energy is cascaded to the dissipation scale, everything falls down from the fountain. And now we want to look really microscopically what's happening at the beginning and how it propagates outwards. So we start with the energy injection, and we use exactly the same force as Lena used in 3D gases. So we use just the magnetic field gradient. And as we shake the gas, the most obvious thing to check is, okay, what's the center of mass motion? And driving the gas with different strengths, we see clearly nonlinear behavior, that the resonant curve changes from underdamped to overdamped. So that's the first thing, that we know that something is going on, energy needs to be going somewhere. And now if we study the center of mass motion, we can select the reactive part and the absorptive part. And obviously, as we are interested in energy injection, we'll focus now on the absorptive part. Now, microscopically, what does it mean? Where do we couple? As I already mentioned, the first excitations is the dipole phonon mode, which is essentially a cosine along the shaking direction with the wave vector pi over L. And to drive such a transition resonantly, it corresponds to the frequency which equals to the wave vector times the Bogoliubov speed of sound. And from this point on, we'll again only drive system on resonance to simplify all the analysis. And the second question coming from nonlinearity is that as this excitation is gapped and we start with a pure superfluid, it essentially means that the energy needs to be pumped up in the energy, not down. So it already suggests that some sort of cascade behavior. And this first step was already studied with our group. You can find the reference here. So as we inject energy, we can go one step further and look in detail at what kind of flux we inject by monitoring this absorptive part. And we can give the dimensional drive strength, which is normalized by the chemical potential, and we can define the dimensionless flux, which is normalized by the chemical potential and the resonant frequency, which are natural scales of the system. And what we got was pretty surprising at the beginning, because the curve for the dimensionless flux versus dimensionless force was universal for different box parameters, for different interaction strength, and for different atom numbers. And it was not only universal, but it was also in clear contrast to a linear response, where we have the force proportional to P, which is our drive, and velocity also proportional to P. Here, our velocity is proportional to the cubic root, which agrees with the classical cubic nonlinearity, which is present in the system. So as we inject energy, there is a natural way to go, so to check whether we have turbulence. So we drive the gas for quite some time, and if we drive it with P larger than half, we find that we have the isotropic momentum distribution at high K, as it is shown here. These are the integrated along one direction time of flight spectra. And if we want to boost our signal to noise ratio for the future, we also find the power law momentum distribution with gamma, which is quite robust, again, against changing the experimental parameters, drive strength, interaction energy, box size. But this time is very different from the weak wave turbulence prediction, because it's 2.9 while we expect 2. 2D is a weird dimension in many regards, and it's also a weird dimension for wave turbulence, as the k to the -2 is also the equipartition energy spectrum, which is an equilibrium distribution, so there is no flux of energy. So at least to allow some flux, there are big corrections on the power law, which makes the turbulence cascades, the power law from the turbulence cascade steeper. But obviously the reasons can be different. That's just one of them, which we know that it shouldn't be 2 in our measurements. But as I mentioned before, gamma is related to beta. So at the end, when we find how the cascade propagates in the momentum space, we can check the consistency of our results. Okay, so now we go to the microscopy. So now we start again from the beginning and try to see our in situ density modulations to check where the energy goes after we drive the first phonon. And by observing the density modulation, actually what's happening is that the density reveals the excitation through the interference with the uniform condensate. So then the question is how to decompose such density, and we use principal component analysis, which essentially provides the eigenbases which corresponds to modes which correspond to the largest variance within the sample. And not surprisingly, if we look at the first mode, we find the first phonon oscillating at the proper frequency. And here we have also the relative weight, and we see that we see 4 significant modes, and then everything sort of saturates, and we also don't see there any shape in space or in time. But if we focus on this first 4 modes, what we see is that we see next phonon modes, but all along one direction. And also not only the spatial form agrees, but also the appearance of the next phonon marks the appearance of the next temporal harmonic. So we can see that in the second mode, we predominantly see the second harmonic. And we can also focus a little bit on the delay, such that the first mode is occupied already at the half driving period, while the second one is populated only after first one is significantly populated. But it's experimentally, it's impossible to say something more, that it seems that there is a delay. For higher phonon modes, it gets a little bit more tricky, because the third one is the odd mode, so we also weakly off resonantly drive it. So apart from the third harmonic, there is also an influence of the first harmonic. And the fourth one is weakly populated, so again, we see some also second order interference effects. So apart from this diagonal terms, which correspond to the resonant phonons, such that the phonon has the resonant shape and the resonant temporal function, we also see this off-resonant ones, which correspond to either the two phonon interference or the direct off-resonant drive. So we saw sort of 1D cascade, and we have to, I have to admit that this is still very deeply in the phonon regime, because for KF, so the last mode we see, corresponds just to 0.15 of KXI. And so deeply in the phonon regime, the cross-directional coupling is suppressed when the free wave interactions are dominant, and free wave interactions means that two phonons combine to the next one, and this is the dominant process in the presence of condensate. So this was all expected, but I promised also some isotropy. So to move forward, PCA doesn't give us any information because there is just noise. So to go beyond that, we perform Bragg spectroscopy. It is a two-photon process, which is velocity selective and allows to directly measure one-dimensional momentum distribution. So if the thing which we saw in the PCA is, let's say, also visible in Bragg, what we would expect is along the shaking direction that the distribution will be wider, and across the shaking direction it will be more peaked, but at the wings both should agree. We did such an experiment, and indeed we saw exactly what we expected, that there is a difference at low K, but at large K, both momentum distribution both along and across the shaking direction is the same and is above the unshaken cloud, which means that the cascade already reached there. And one can see that here the KXI is roughly equal to 1 inverse micron, which marks the point where essentially the distribution starts getting isotropic, which also makes sense from these ideas which I mentioned about the phonons and free wave coupling, because at KXI the excitations of the system start behaving like free particles. So having established this isotropy already after one driving period, we can now focus on the cascade and how it propagates at high K towards the dissipation scale. So this is the compensated momentum spectrum, compensated with the power law. taking at different times of shaking. And we can clearly see the cascade that it propagates in K-space up to the dissipation scale when it saturates and the momentum distribution is stable. So we can use the knowledge which we build up through the beginning of the talk. So first of all, we can calculate the energy in the cascade. And this is simply done by multiplying the spectra with the kinetic energy and integrating it. And then you can see what's the rate of the increase of energy as the cascade is formed. And you can see that it agrees pretty well with our dimensionless flux and our universal function. Secondly, we also can predict beta. And the predicted beta again agrees with how the cascade front propagates in momentum space, and then it saturates at the dissipation scale set by our trap depth. This gray shaded region corresponds to the independent estimate based on the light measurements of our box trap. So now, really, as a cherry on top, we can fit our beta by fitting this previous this KCF here, the cascade front, and use our gamma to perform the scaling and to show that the momentum distribution is indeed self-similar. So when we do that, we see that all the pre-steady state curves collapse on top of each other, while the steady state ones obviously are not in the scaling region and show that the scaling breaks down and they stick out. Additionally, we can check the consistency of our measurements using the R beta and gamma. We can use again the same formula to get the dimensionality of the system which agrees with the dimensionality of 2. So with this, I would like to summarize what I just shown. So we report on the observation of the two-dimensional direct cascade in a Bose gas, and we show 2 key components of the birth of turbulence. So the emergence of isotropy under continuous anisotropic drive and the dynamic scaling in the pre-steady state. Regarding the outlook, there are multiple directions where one could go. One obvious one is to study similar dynamics, but in the relaxation and to see how the coherence emerges. Also, one can also think about the situations when the cascade is not necessarily isotropic. One could imagine, let's say, giving some velocity, so forcing the gas through the channel and having some net momentum flux, which will break the isotropy. And finally, this is probably the most frapping part, is that we can study the interplay between vortex and wave turbulence, because Bose gas support both vorticity and waves. And with this, I would like to acknowledge both teams. So the equation of state is obviously Lena and Gevorg, Yiji, Alek, Jake, Chris, Timon, and Rob. And from the two-dimensional side is Panos, Martin, Andre, Julian, and Nishant. And Zoran was obviously involved in all of this. And with this, I would like to thank you for your attention.
Thank you very much for an excellent talk, both of you. And I believe we've already got a question. Giorgio, do you want to start?
Yes, yeah. Thank you, Maciej, for the nice talk, and I'm really excited to hear and see the nice results. So I have basically one question and a comment. So we'll start with the question that is probably simpler. So with the forcing, you are basically shaking the trap. Okay, so
Yes.
So you say that you are forcing by a linear resonance, and we have expected to have a parametric resonance. You think about that what the forcing is just a potential that is oscillating that multiplies psi. Naturally, in this kind of system, it's a parametric, so you will expect a frequency excited at half of the shaking. You see what I mean? So take an oscillator and I'll just make it forcing or oscillating like this, okay? And not an additive term, but just something like the one of the coupling constants.
Yes, are you referring to just shaking with, let's say, the interaction energy, and that would be, for example, some parametric resonance that?
Yeah, but I think you shake with omega f. I would have expected you are exciting in the system to omega f by divided by 2.
I think
It's available.
I think that this would happen if you would shake with, but I'm not exactly sure that you because what we here do we directly couple to this first excited state, so we couple resonantly just, but if I think we would shake the interaction strength, so we would change the interaction strength, we would change G tilde dynamically, I think then this parametric resonance would appear. That you change the interaction energy, so you shift this potential, and then you can get the pairs of opposite direction phonons of free particles depending on the frequency. But I think then I would expect the half.
Yeah. Thank you. And the second is a comment that maybe you're not aware. We recently, so now it's accepted, have a new theory for 2D acoustic turbulence. It is the work that we did with Sergei Nazarenko, Viktor Lvov, and Adam Griffin, the former Sergei's postdoc. So it's you know that 2D acoustic turbulence is really pathological. So something that you mentioned, that waves actually, because the resonant manifold, they are always parallel. Okay, so that is what explains the anisotropy, and that makes 2D acoustic turbulence in principle very bad. So it is not really well defined, except for a BEC, where you have a dispersive length that can regularize everything. So if you account for this, you can also heal the theory and get an effective theory that is, let's say, exact. Okay, so it's a different kinetic equation, and the outcome is that you can exactly compute the Kolmogorov-Sakharov solution, including the constants. And so the nice thing that the scaling that you expect is k to the -3 in the acoustic 2D. That is pretty much what you observe. So I can send you the reference. It's going to appear on a PRL in a couple of weeks, month. I don't know, but it has been accepted.
Yes, I think I saw it at some point on arXiv, but well, I can tell you why I thought that our results, even if they are 2.9, I fully agree that this might be some interplay between, because that's how I feel that this is some interplay between the phonons and free particles, and that's probably why the exponent is different. But at this high k part, when we derive this equation for beta versus gamma, we assume that we have free particles.
Yes,
that's why it was that I agree that the exponent itself, because there is a presence of phonons and everything, but this front of the cascade, it seems more free particle like.
So that maybe I misunderstood something, because the last part of your talk was more on the acoustic part, on the phonon cascade, 3 waves, or I missed something.
Well, yeah, the dynamic scaling was on the free particles. It was already above take side.
Okay.
This all in situ was super low. This I agree that it's on that was on the. Well, I can show what was on
So maybe I misunderstood something.
This part was all about the acoustic part. Yes.
I can't see anything.
Wait, am I not sharing the screen?
No, you're not.
Sorry. I thought that I was. Sorry. Okay, do you see now?
Yep.
Okay, great. So this is clearly acoustic. Yes.
Yep. And you see the anisotropy that is preserved by the
yes. So that's the acoustic part. And then when I go forward, so in K space, so we go here k psi is at 1. And then when we talk about the dynamic scaling, we already start at 1.5 or 2. So we are in the free particle regime for the dynamic scaling. Because experimentally it's hard, because what you measure in the end are free particles when you take the snapshot. So Yes, but I agree that the power law can definitely be influenced by the
Yeah.
fact that there are a lot of phonons and there is a lot of acoustic stuff going on, and maybe it's just that we see the cascade here are free particles, but at lower case there is an acoustic cascade which maybe sets the resulting power
Any
law.
chance to getting a steady state of acoustic wave turbulence?
Well, in principle, let's say we see something that these oscillations are a steady state but my problem is that I don't know, but maybe the theory is now somehow deals with that, because I don't know, these are not random waves, yes, at this moment when we start just shaking like this.
But it doesn't really matter, because everything takes place on rays in the it's because it should not make a problem actually for the theory.
I see. I thought that always that it needs to be random waves, because otherwise there was always some this random phases.
Yes, but it's actually in 2D what's going on is the phases what you expect to be random basically, but in 2D, because of the resonant condition, at the end everything is translated into rays that could be random, okay, and in principle, but if you put something in one direction, it will go in that direction.
Yes.
Okay, because they cannot, it's just, so basically acoustic is just driving in one line and dispersion is slightly moving apart, okay?
Yes.
And all acoustic regime, if you start with something that is anisotropic, okay, it will stay like this. And I think it shouldn't be a big problem.
I see. Okay. We also got that basically this, but it would be very nice to have, let's say, more, but we also saw that if we look at the, let's say, this amplitude, it looks a bit like power law, but the power law from 4 points is never strong. So we thought that it's not necessarily that, but we'll definitely look into it, because it seems very interesting actually.
Absolutely nice, very nice experiments. Good. Thank you.
Thank you.
Are there any other questions? If you want to raise your hand. I have a quick question for Nina. You had, when you were talking about quenching between two different driving strengths, and you had a nice plot that shows the system switching back and forth between the two next to a light switch. There's a bit of a time lag, or it's not an instantaneous switch. What sets that time scale?
So actually, it's actually what Maciek is shown afterwards. When starting from equilibrium, we have the similar thing when we switch between different states, because really the system needs some time for this increased energy flux to propagate through all the way up to the trap depth. So when I showed the additional cascade population propagating outwards to higher momenta over time, that exactly set the time scale of the switching time.
Okay. Thank you. Oh, we have one more question by Davide.
Yeah, thank you. I think it's a question for both. So thanks first of all about for your nice talks and presenting these nice experiments. So my question is about the Healing length scale. So clearly, you've shown that you can measure the dispersion relation, so you can estimate the Healing length scale. I think at the beginning of the experiment. But what is happening when you start forcing? So do you lose particles in the condensate mode, K0 mode? So does the Healing length stay the same, or do you have any idea if that changes? And so you can also shift from, say, 3-wave to 4 waves interaction.
Okay, I think I can answer that. Basically the healing length changes because we always deplete our condensate. So there is this change that the healing length will change and goes towards smaller and smaller case. And this is also, well, if you look here at the momentum distribution, yes, you see that the occupation at k equals 0 is almost half. And essentially what, if we would take the similar spectrum at later times, we would see that actually they are coming closer and closer to each other. So it means that the isotropy is established at, let's say, earlier k. But it always there is a little bit anisotropy at the super low case, as I showed with PCA. But this intermediate, it comes back from 1, then it's at, I don't know, 0.75, but this we haven't studied in detail. But we see that this isotropy also goes down. So maybe, so I think this also hints that actually this healing length also goes down.
So if the healing length goes down, that means that you're
Sorry,
more and more
sorry,
in the 4-wave regime,
yes,
in the free particle regime, right? Okay.
Yes. I think I messed up a little bit inverse healing length with the healing length.
Okay.
Yeah, but you're right. Yes.
Okay, so that's stronger evidence that you are in that regime and not in the fully acoustic regime. Okay.
Yes.
Thank you.
Yeah,
Thanks.
yeah, I think that's a bit more enlightening answer. In 3D, we found it quite difficult to find a way to figure out which one we have more. I think the only one thing I can maybe add is that when we see our result for the equation of state, which changes slope a little bit, a slope that would sort of be in the middle of this range is actually the slope that's predicted for the 3 waves. So it wouldn't be super far-fetched, but what confuses us is that generally we would at the lowest amplitudes more expect a slope. So we would expect our plot to bend the other way if there were really a crossover between 3-wave and 4-wave as a function of depleting the condensate. But it's true that we do deplete it quite a lot, and actually we are quite surprised that things being this equation of state doesn't break down even when more than half of the atoms are already in the cascade region. So it's that much about 3D.
Thank you. I also had another question, which was something that you probably now answered, because it was about the 2 predictions for the equation of states, and you said that the other prediction would come from the 3-wave, so the fully acoustic wave turbulence. Is that where the other exponent would come from, if I got it right?
No, for acoustic, I think it's even different. So
it's even different. Okay, so because you show 2 different numbers. So one, you said that it was from wave turbulence, and what is the other prediction? Where does the other prediction come from?
So for wave turbulence, if we take this formalism from Zakharov and related people, then we have these scattering equations, the scattering integral, which sets the flux. And if we plug in the free particle dispersion, but then still we have to make a difference of, do we consider 3-wave or 4-wave scattering processes? And that gives this exponent of 1/3 versus the other prediction would be 1/2, but that's both in this perturbative weak wave turbulence theory. And then on the very other side,
for the free particle
GPE, right, which we're trying to.
Okay. Thank you. Thank you, Lena.